number 9 of your textbook, which is flow over immersed body. So basically, as we discussed in the last class, that this chapter is concerned with the generally about the characteristics of external flow. So it means that there is a body which is placed in a flow field, and the flow is going over it. So chapter number 8 was concerned about internal flows, and this chapter is concerned about external flows. So there are certain characteristics of flow which we need to determine or discuss and analyze in case of external flow. So two major characteristics are lift and drag force. So drag force is the component of force which is so it is basically just a brief recap of the last class. So drag force is the component of force parallel to the flow direction, while the lift force is generally it is perpendicular to the flow direction. So and we can determine the drag and lift force by doing the integration on a differential element, and we discussed it in last class. And then we can represent these two forces in terms of non-dimensional term like Cl, which is coefficient of lift, and Ct, which is coefficient of drag. So both are kind of dimensionless properties, and we define it because we want to mention that how much drag would be there or lift would be there depending upon the shape of geometry rather than the area. Because here, if you see that we have kind of cancelled out the area, because lift force would be directly proportional to area, and drag force is also directly proportional to area. So in a way, we are considering the effect of area. So it means that it only depends on the shape or orientation. So then in the last class we also discussed that since drag coefficient for a blunt body like this Toyota Scion would be higher as compared to some racing car like this racing car on the right hand side. And then for the aerofoil, and we also discussed in the last class that there are two types of bodies. One is streamlined body like aerofoil, or blunt bodies in which the frontal area is more. So then we discussed that CD values are calculated for different kind of geometries. Here they are on this slide. They are two-dimensional bodies, and then here there are certain two-dimensional and three-dimensional bodies. So we can calculate CD as a function of Reynolds number, right? So uh, uh, we can conduct some numerical experiments to get the value of CD for different types of geometry, and then CL as well. So now we are going to, in this class, we are going to discuss the characteristics of flow on different kind of geometry. So now we are going to talk about two types of geometry. As I mentioned, one is streamline bodies, and second is blunt bodies. So in this we are going to discuss certain parameters. One is uh, okay those characteristics which I am talking about. One is viscous effects, then wave region, then flow separation, and uh, fourth one can be boundary layer thickness. Boundary layer thickness. So these are some of the important characteristics of flow when we talk about external flow. So first of all, we discuss the streamline body. So what is a streamline body? The frontal in the case where we so I'm going to talk about streamline body. So what is the example of streamline body? A flat plate placed we can say a thin flat plate placed parallel to flow direction, right? So let me show you that how these properties which I have shown here, A, B, C, D, how they change when we kind of increase the speed of flow. So for that, I'm going to put a picture here. So just hang me for a while, so I will explain it. Okay. So this is the figure. I hope that you can see it quite easily. So now, this is the flat plate which is placed parallel to the flow. So it means that the flow is coming from the right hand side. So we are talking about, at the moment, we are talking about this figure, which is figure A, right? So here the Reynolds number is 0.1. 0.1 means that because Reynolds number, we know that that is the ratio of inertial forces divided by viscous force. Now you can see that if Reynolds number is 0.1, so it means that the viscous forces is quite significant as compared to inertial forces. If the viscous forces would be 10 times more than inertial forces. So this gray region, this one, which is shown by gray shaded region, that shows us the area in which viscous effects are dominant. So we can see a larger area around this flat plate that has strong viscous effects, right? And then boundary layer thickness, you can also see that that is quite boundary layer thickness. How we can define? And let me show it here. That boundary layer thickness is this distance. Where the viscous effects become negligible, that is the thickness. So inside the boundary layer, viscous effects are very high, and you can see that boundary layer thickness is increasing as we move along the flat layer, and that's what we are studying. And then there is a very large wake region here. Wake region is the region downstream. Downstream is this location. This is downstream location, and in this we can see that this is the wake region thickness. This is wake region, right? So wave region is very high, boundary layer thickness is very high, and then is there any flow separation? No, because it is a streamlined body, so there is no flow separation at all for the flow past streamlined body. So negligible flow separation. Right. Now, this figure, which is the figure B, now when we talk about this, here the Reynolds number is kind of 10. So it means that now the viscous effects are 10 times less than the inertial effects. Inertial effects mean that the forces due to inertia are which are kind of producing some kind of acceleration. So now you can see that the viscous region, which was shown by the gray area, it is quite thin now. So viscous effects are going to be limited in a very small area near that in the vicinity of the flat plate. Then the wake region, which is on the downstream region, that is also quite less. And then there is still no flow separation, because flow separation doesn't occur in the flow over a streamlined body. And now if we increase the Reynolds number even more, like if we make it 10 million, so if we make it 10 million, now you can see that viscous effects are, in fact, they are limited very near to the wall. So it means that the inertial effects are very dominant in this case, because viscosity effects are kind of limited in that area. So boundary layer thickness has been reduced, wake region has been reduced, and the streamline reflection, that is very less, because you can see here, right? So this is the boundary layer thickness. Now, this was the case when we talked about the flow over a streamlined body. Now, if we talk about flow over semi-blunt body, semi-blunt body mean or okay. Now we are going to talk about semi-blunt body. Semi-blunt body, it is kind of flow over sphere or cylinder. Why we call it semi-blunt? Because fully blunt body is a flat plate which is parallel to the flow direction. So that is kind of fully blunt body, and this is fully blunt body. And if we are talking about cylinder which is placed in the flow. So and the flow is coming from here. So it means that there is kind of a gradual divergence of the streamline. But here, if you can see, it would be suddenly diverging in this direction, the streamline, right? If the Reynolds number is low, right? So we are going to talk about semi-blunt bodies for the time being. So let me show you that. Let me place that diagram here as well. So let me just a minute. Okay, so now again we are going to talk about different cases depending upon the Reynolds number. So if you look at the figure number A, which is I am talking about this figure, which is figure A, and you can see that Reynolds number here it is written. If it is not visible, I am going to write it. Reynolds number 0.1. So it again means that the viscous forces are dominant. So now you can see that even for the flow over cylinder, there is no flow separation. Viscous region is quite large, which is shown by this kind of shaded region. So viscous effects are quite high. So that's why that region is very large. And then there is another thing that the streamlines are symmetrical. Let me write. Streamlines are symmetrical. How they are symmetrical? If I draw a vertical line from here, from the center, now you can see that whatever the streamline was here, the mirror image is on the right hand side. So the flow is kind of symmetrical, and then there is no flow separation. You can see that the flow which is coming here, that is being perfectly attached, and then it leaves the area, right? So there is effectively no wake region. Why is that? Because the velocity is almost same as the free stream velocity as we move from here, right? But if we increase the Reynolds number to, I think it is at 50. Here it is written Reynolds number 50. Right? So it means that in this case, viscous forces are 50 times weaker than the inertial forces or the flow momentum forces. So in this case, you can see that first of all, streamlines are no more symmetrical. You can easily see that on the front we have got streamline like this, and on the back end we have got there is a flow separation region. We call it separation bubble. Separation bubble. It means that there is a region which is a fixed region in the downstream area where the flow has been separated from this surface of the cylinder, right? So now what means that pressure drag would be very high, it would be very significant. In this case, there wouldn't be any pressure drag because whatever the pressure would be on the front, almost it would be the same pressure on the backhand side, but maybe it would be a little bit less, but that pressure drag component would be very less, but friction drag component would be very high because the flow has been attached at the surface, so shear forces would be higher. But in this case, because there is a separated region here, so it means that there is no fluid here, so maximum pressure would be here, which is the stagnation pressure, and here we would have vacuum pressure or negative pressure. So that's why pressure drag component would be very high. Okay, if I go towards the flow, oh, sorry, flow over flat plate. Now, in this case, in all the cases, the major component of drag would be due to friction drag. Let me write friction drag. Why is that? Because in all the cases, there is no flow separation, and all the drag force would be applied by this solid surface by the with the help of wall shear stress, which is on this solid surface. Right. So here there is only one component, which is friction drag. Now coming back to the this uh, these cases. Now we were on figure B where the Reynolds number was 50. Now here I have told you that we would have a vague region. So you can see that here the viscous region is quite unsymmetrical. On the front side it is very limited, but on the back side we have got viscous region as well as vague region. So this is our viscous region, or we can also call it kind of weak region. Now, if we increase the Reynolds number even more, like Reynolds number is equal to 1 million. So now you can see that in front of that body, the viscous effects are limited to very minute area. Let me show you this area. So you can see that the shaded region is very thin on the front end side. Right? So it means that the boundary layer has been also very shrunk. So it means that in majority of the region, the inertial effects are more. And then we have got some kind of vortex generation here. And we call it von Karman shedding. So it means that there is no fixed vortex or separation bubble. Instead, there is that bubble kind of moves with the flow due to inertia. And maybe in the next class, I would also show you some animation of those von Karman shedding. So it would be more clear to you that how these vortices move in the downstream region. Right. So here we have in these cases in Reynolds number 50 and 1 million, there is a flow separation on the back end of the semi-fluid body, and due to that pressure drag is very high in these two cases. But for the low Reynolds number, pressure drag is negligible and friction drag is more. So if I write that these discussion points here, if I can kind of summarize them, maybe it would be more helpful. That for flat plate, for flat plate flow, when we have got parallel flow over flat plate, parallel flow over flat plate, we have got viscous effects are dominant at low Reynolds number. And so this is first point. Then second point is that inertial effects become stronger with increase in Reynolds number. Then we have got no flow separation. Then the consequence of that is that uh, uh, that friction drag is maximum and pressure drag is minimum. Right. And then the last point we can say here that boundary layer thickness reduce with increase in Reynolds number. Right. So these are the five conclusions which we have seen from the figure which I have discussed in detail, which was the first figure we discussed in the detail. Now talking about the external flows over cylinder or sphere, we can do semi-fluid body. We can say that at very low Reynolds number, no flow separation and friction drag is maximum. Then at moderate high Reynolds number, there is flow separation and wake region in downstream location, and pressure drag becomes dominant. Then again, streamlines are symmetrical for low Reynolds number and non-symmetrical for high Reynolds number. Right. And then again the boundary layer thickness decreases as we increase the Reynolds number. So that are the kind of characteristics which we have seen up to now for the flow past blunt bodies, semi-blunt bodies, and flow past a streamline object or body. Right. So with this discussion, the separation region, wake region, I have shown you on the whiteboard as well by marking those regions, and presence of separation region and wake region at moderate height Reynolds number and the velocity gradient within the boundary layer. They are more when we have got higher Reynolds number, because if this area is thin, it means that the velocity is changing from 0 to the maximum value in a very thin region. So that's why velocity gradients are very high when Reynolds number is high, right? So that is why, due to that velocity gradient, there is a more shear stress, because the shear stress is mu into du dy. Du dy is the velocity gradient. Right. So this is kind of an experimental visualization of flow around a sphere. So we can also kind of take it as Earth, but of course this is not a visualization of Earth. Rather than this, this is a sphere in an experimental setup, and you can notice the figure on the upper side, it is at very low Reynolds number, and you can easily see this is the wake region. This is the white region which is at the back end. This is kind of a wake region which is shown here. But this wake region becomes very small in the bottom figure, where we have got higher Reynolds number. So in higher Reynolds number, the thickness of the wake region becomes small as compared to the thickness of wake region in the upper, in the case when the Reynolds number is low. What is the reason for that? Maybe I would discuss in detail in the next lecture. So, but just to give you a hint, that is dependent on the boundary layer separation point. In case of laminar flow, we would have boundary layer separation occurring at this point, right, somewhere here. And if we measure theta from here anti-clockwise, so at theta is equal to 80 degrees, there would be a flow separation. But when the flow is laminar, we are talking about that. But when we have got turbulent boundary layer, then the flow separation occurs here at theta is equal to 140 degrees. When theta is measured from this axis anti-clockwise, so you can see flow separation is delayed. So that is the only reason we put dimples on the surface of a golf ball, because we want this wake region to be much smaller, and so that pressure drag is smaller, and that's why we want it to travel more inside the in the air. When the pressure drag would be less, then it means that the ball would travel more, and that is the only reason there is a phenomena of reverse swing in cricket ball, because in that as well, on one side of the ball is kept shiny and the other one is made rough. So on the rough side, the flow becomes turbulent and the boundary layer becomes attached, and on the shiny side, the flow remains laminar and the boundary layer separates somewhere here. So there would be a vertical pressure difference as well. So that's why the ball moves in here. So that is basically the entire phenomena of reverse swing, that we kind of make one side shiny so that the boundary layer would remain laminar, and it separates at theta is equal to 80 degree, while the other side which is rough, that becomes boundary layer becomes turbulent and it remains attached. So that's why the flow separation happens as theta is equal to 140 degree. So there would be kind of a, on one side we have got a vacuum due to flow separation, on the other side we have got flow attachment due to turbulent boundary layer. So that's why there would be a, if the upper side is shiny and the lower side is rough, so the ball would always travel towards the shiny side, because the shiny side has got flow separation and the rough side has got boundary layer attached due to turbulence. So that is the case of reverse swing in cricket ball. Okay, so and that is the other reason that we create patches on football ball, because we also want to have that turbulent effect, so that that the kick of the ball would travel the ball quite far away in the air. So that, because if the flow is turbulent inside the boundary layer, the wake region would be less. Okay, so now we quickly go through the drag and lift forces, which we discussed in quite detail in the last lecture and as well as in this lecture. So drag offers, what is a drag force? Drag force is basically the resistance to the flow in the direction of flow due to the pressure and shear forces on the surface of the object. So drag is the result of two types of forces. One is pressure force, which is kind of normal force, and shear force, which is kind of parallel to the flow direction, and pressure force is the normal force which is perpendicular to the flow direction. Right. So two types of drag forces, as we mentioned on the in the previous lecture as well, that there are two types of drag forces. What are those two types? As we discussed in the last class, one was uh, let me write it here. One is friction drag, and we also call it skin friction drag, because it happens on the surface of that on the surface of that body. So that's why we also call it skin friction drag, right? And that is due to so skin friction and drag is due to the shear stress acting on the surface, right? And that would be more important when we have got streamlined bodies. So streamlined bodies like a flat plate which is placed, a thin flat plate which is placed parallel to the flow direction. So it means that there wouldn't be any pressure drag, because the frontal area is very small and there is no flow separation. So that is why we have got kind of only the skin friction drag. And then the second component which is there, that is pressure drag component. Pressure drag, and we also call it form drag, because it strongly depends on the shape and geometry of the body, and that is due to the pressure difference in front and back of object. Back of object, right? So that was and it is usually happens when we have got the flow over a blood body or semi-blunt bodies for that matter. Like here, this is a fully blunt body, so it means that this is a flat plate which is perpendicular to the flow direction. Now, what happens that the flow comes here, and because it is a blunt body, so the streamline divergence would be very significant, and due to that effect, there would be some kind of break region or flow separation region at the back side of the that low pressure region. So it means that when on the front side we have got stagnation points, so high pressure region and low pressure region due to flow separation. So that gives rise to this difference in pressure gives rise to a net force which is acting on the positive x direction. So that is the force which is exerted by the fluid on this body, right? So that is the drag. That is the force which is acted on this, and the equal force would be applied by this object on the floor. So that would be the drag force, right? So pressure drag is more dominant in blunt or semi-blunt bodies, and friction drag is more important when we have got streamlined bodies there, when there is no flow separation, right? So the friction drag is the component of the wall shear force acting in the flow direction, and then it is function of not only magnitude of the wall shear stress but also the orientation, that if it is parallel or if it is an angle to the flow, right? So angle of attack, which we usually call it. So the friction drag is equal to 0 for a body placed perpendicular and maximum for the flared surface parallel to the flow. Then the friction drag is also proportional to the surface area. If the surface area of this flat plate is more, then we have got more friction drag, right? So it is directly proportional to the surface area. And then it also depends upon the viscosity. Why is that? Because wall shear stress is mu into du dy. So mu is the viscosity. So as I was saying that friction drag is directly proportional to area, you can always see that friction area is in the denominator and it would be multiplied here. So force is friction, and that force due to that frictional effect would be directly proportional to surface area, right? So friction drag contribution is generally higher for the streamlined bodies, or even for the blunt bodies if the flow Reynolds number is low. Reason for that is that flow would remain attached, and all, as we discussed here in the case of cylindrical bodies, that the flow would remain attached. So all the and the pressure difference between front and back is very small in this figure A. So that's why in this figure A, the major component of drag would come from friction drag, right? So this was it for the friction drag, and now the pressure drag is the part of the drag that is directly due to the pressure difference on the. It should be pressure difference on the object, and it strongly depends on the shape and form of the object. So that's why we also call it form drag, right? So it depends on the geometry or shape of that body, and it is a function of magnitude of pressure. So that is understandable, and orientation of the surface. Pressure drag on a blunt body is higher than streamlined body at a higher Reynolds number, because there is a flow wake region or flow separation region at the back end of the object, like here, because there is a low pressure region at the back end. So, and on the front we have got higher pressure region due to stagnation point. So that's why it would be higher. Okay, and then it can be determined by the coefficient of drag, that is pressure drag component. That is this is the force due to pressure difference, and then half rho u squared upon area. And total drag on geometry would be the sum of pressure drag and friction drag. So, and total drag force would be again the summation of drag force due to friction and drag force due to pressure difference. Right, and here if we see that here the CD, which is a coefficient of drag, it is shown for two cases. One is flat plate normal to the flow, and then the other one flat plate parallel to the flow. And so you can easily see that we have got L upon D. When L upon D is a very small value, so it means that we are talking about a plate which is parallel to the flow, right? When L upon D is quite small, then it would be flow due flow parallel plate, which is the plate which is placed perpendicular to the flow. But when L upon D value is very large, then it means that the length of the plate is more as compared to the height of that plate. So it means that now, which means we are talking about flat plate perpendicular to the parallel to the flow, right? So in both cases, we can see is that the CD value changes, and here the Reynolds number is 10 to power 1 lakh, right? So you can see that the variation is it means that CD value when L upon D is less, which means that we are talking about the a plate which is placed parallel to the flow. It means that the flow is that the body is quite blunt. Frontal area is more. Then in that case, CD value is very high. Like CD value would be around 2 or maybe 2.5 for that case, right? So if you see here that when L upon D is 0, what does it mean? That the flat plate is normal to the plate. But as we increase L upon D ratio, it means that we are going towards when L upon D is equal to 1, what does it mean that we are talking about the flow over a cylinder? Because in that case, this L would also be equal to diameter, right? So so it means that if the flow passes through a blunt body or semi-blunt body, the CD value is more. But if the body becomes more and more streamlined, then the coefficient of drag reduces. So that is why we usually make Formula One racing car more streamlined bodies, so that coefficient of drag is less and total drag force due to that would be less. Right. So this curve explains very nicely that for a blunt body, the drag force would be higher, but as we increase L upon D, it means that we are increasing the length of the body as compared to its thickness or height. Then it means that its total drag force would be less. And when L upon D is kind of 6, it means that that is kind of flat plate parallel to the flow. Here it is given to us. So in that case, we can easily see that drag force is even less than 0.5, maybe around 0.1. So it means that as an engineer, if we are designing a vehicle, then we kind of reduce the frontal area and we want to make it the body more kind of a streamlined body or very thin body if possible, right? So here it is very, it has got the example here. You can see that there is cylinder here on the left hand side who has got a diameter d, and then we have got a streamlined body on which we have the maximum height is 10d, right? But interestingly, very interestingly, drag of this small cylinder is equal to the drag force of this big airfoil. Why is that? Because in this case there is a flow separation and Reynolds number is quite high. So you can easily see that drag force they are equal. CD value for the cylinder is 1.2 and CD for this aerofoil is 0.12. So you can easily see that the effect of making a body thin or streamlined, because the flow separation is very small or negligible in case of aerofoil or streamlined body. So the majority of the drag at the higher Reynolds number is due to pressure drag. So that is very small in case of streamlined body. So that's why this small cylinder would require the same drag force as compared to this big aerofoil. So that is the significance of making a body streamlined, right? So then I think from here we will talk in the next class. So if there so maybe up till here. So this is the how we can reduce the drag force. As I mentioned that we make the body streamlined, then the drag force reduces. Like this for this aerofoil or this small cylinder, they are very small, and this cylinder is very small, and even this aerofoil is very big. This is the drag forces here. So you can see that they are quite compatible. But if the cylinder is big and the Reynolds number is even higher, then you can see that the drag force is more. Here the shaded region is due to skin friction drag, and this empty region is due to pressure drag. So pressure drag, you can see in almost all cases, this pressure drag is the major contributor to the total drag force. So we want to reduce pressure drag because that is very critical. That skin friction drag is only maybe 1 to 5% of the total drag, right? You can see the shaded region even here. It is very small as compared to this non-shaded region, right? Pressure drag. So in designing any object, in case of external flow, we want to reduce the pressure drag. So that's why we put dimples on the golf ball, because dimple on the golf ball would reduce the pressure drag.